all the presenters, everyone that attends this conference is so friendly, so willing to teach, so willing to learn from you too. So it's not just watching these videos, it's kind of getting that insight afterwards and around at dinner, at drinks, like all the other aspects of the conference besides just like that technical information.
Hello everyone, good afternoon. My name is Caro Campos. I'm a R&D team lead at JFrog and I work at the content team. And today I'm going to be talking about shared libraries and specifically where to find them. You know, as part of the content team, you bet that we do encounter situations with shared libraries every day. So let's get to it. Today I'm going to be facing libraries from a point of view of, you know, they're a file. There are files on disk that they contain compiled code, right? The word library, I'm using it like loosely because it does have different meanings in different contexts, but in this context, it's just like files in the file system that are needed at certain points. So these are just some examples of how developers deal with shared libraries. This was posted maybe a little over 16 days ago on Stack Overflow. A user that built an application on Windows, and then when they wanted to run it, they couldn't find in particular, I think the import library when built in the DLL. Here, an Apple developer, I think this was for iOS, that they couldn't find a library for a framework that they were using. Frameworks on macOS also contain shared libraries. Similar problems on Linux as well. And I think if you're a Windows developer, you may have seen an error like this in the past. So what I was surprised to see when I was looking for this error in Stack Overflow is that a lot of them were actually recent, right? So if I could say so myself, these errors are experienced not only by people who are new to C++ development, but also by experienced developers as well. So this is something that's very actually common to see. So what I'm going to be covering in this talk is basically those 4 points at the top, which is when are shared libraries needed, which programs actually try to locate the libraries, some tooling that's available to like query and troubleshoot how they're being located and which libraries are actually being loaded. And obviously the topic of the talk is where to find shared libraries. What I'm not going to be talking about or covering is any sort of pros and cons of static versus shared linking, the internal structure of shared libraries beyond the header information that contains, you know, the name of the shared library and other dependencies. And I will not be discussing any linker specifics of what happens when a shared library is loaded. So let's move to the first point. When are shared libraries needed? Mainly either of these two tasks here. When you are creating other shared libraries and executables, and when you are running executables, either at the time of launching them or in other specific cases when during runtime you load any loadable plugins. But I would like to say that there's two more processes or tasks that require locating shared libraries. The first one I would like to mention is when we configure the build. So before we actually build anything, our build system may try to locate shared libraries. And at the very end, after we have built everything, we have tested it, we may want to locate shared libraries to package the application for distribution, right? So I'm going to reorder these things in the order in which they occur. So first we need libraries when we configure the build, and then when we're linking libraries and executables, and then when we're running them and when we package them. So I would sort of divide these logically by build and run. And the first part of the talk, I'm going to be focusing on which programs need to locate shared libraries, specifically these two here in the middle, right? When we create other shared libraries and executable, the linker is the application that's going to be needing to locate these files. In some places, it may be called the static linker. Don't be confused in the sense that the static linker happens at build time, but it does consume both static and shared libraries. And when we launch the applications, it is the dynamic linker / loader, depending on the operating system. It may have a different name. It's also called a linker, so it can be confusing, but this is an operating system component that launches our application and loads the shared library dependencies. And at the end of the talk, I'm going to be talking about the first step, what happens when we configure the build and the build tools need to locate shared libraries, and what happens at the very end if we want to package them for distribution. So let's move on to the first example, and I'm going to be talking about what happens on a sort of vanilla GNU Linux here. And we have a very simple program, right? This program calls a function iamfoo, which is in a shared library, and for that shared library, I have a header, which is foo.h, and a libfoo.so, which is installed specifically in those directories. So if I use GCC to build this program, right? Obviously, with that command that I'm showing there, what's going to happen is that GCC is going to complain that it doesn't know how to resolve that symbol. So obviously, you may be familiar with this. The solution is to tell GCC, hey, please link this library to consider the symbols that you need. You may be surprised how easy it is to forget to tell the compiler and eventually the linker which libraries to link. So this is actually a very common problem. And then when I run the program here at the top, then obviously the implementation of this function just prints a message to the console. And now I've shown you basically both stages, right, in those two commands. First, when I invoke GCC, it is the linker that finds libfoo.so based on the -l foo that I pass to the compiler. And in this case, the linker is indirectly invoked by GCC. On Linux in particular, and macOS, I think it's very unlikely that you are going to be invoking the linker directly, and I will show you why. And the linker here is part of the compiler toolchain. Now, when we run the program, it is the runtime linker loader, and on Linux, modern Linux is called ld.so, that it finds that library and then it executes the code inside it. So the runtime linker loader is actually part of the system. This is going to be in pretty much all Linux system. Whereas the static linker, it's only going to be present in your system if you actually have installed it yourself. So that's another distinction. So first, I'm going to be talking about the linker itself. As I mentioned before, it is a program that is invoked by the compiler, in this case in Linux. It's typically called LD. There are other implementations. You may be familiar with Gold, LLD, and Mold. Some of them are like obviously much faster than the BFD linker, which is the default implementation. And as I mentioned before, we don't invoke it directly. This is invoked by GCC. So if we pass the -v for verbosity flag to GCC, at the very end that I'm showing here, it shows an invocation of collect2, which is a program that eventually calls the linker. And we're going to see that while I passed lfoo to GCC, GCC itself passes a lot more flags, forwards a lot more flags to the linker. So we need to keep that in mind. As for how the linker searches for that library, well, we can go to the man pages here. And it tells us specifically what the default search path is or how it is built into the linker. And I'll show you an example later. Obviously, I didn't tell the linker to look in additional directories. So in this case, it's using its default search path. Now, a word of caution when it comes to reading the documentation for the linker. Each Linux distribution or toolchain may actually be configured differently. So if you're on Linux or if you have a GCC that is built for cross-building or something like that, the individual default settings for each linker may actually be different. The defaults mentioned by the documentation of LD may actually be overridden by the invocation from GCC. And this is something that I found in the past, especially on Ubuntu or Debian distros as well. So if you are deep into troubleshooting a linker problem, always check how the linker was actually invoked with -v. And the last word of caution, if you're using other linkers, bear in mind that some of the behaviors I'm going to be talking about that are shown by the linker may be different in the different implementations. So we have BFD, which is the default, Gold, LD, and Mold. They all have like slightly different behaviors that I encountered in the past. So I'm going to show you how to get the default linker to show us where it's searching. So if we pass that flag over there, -x linker tells GCC, please forward that flag to the linker. And I just tell LD, please be verbose. It's going to dump the content of the internal linker script, which is how, it's a file that describes how the link happens for the specific platform or architecture. And there are these search dir statements that actually spell out exactly the directories that are being considered to resolve that link foo library. And we have something similar as well for the dynamic linker loader. And first I'm going to talk about like when I produce an executable on an ELF platform like Linux, although there are other, the full absolute path to the linker loader is actually part of the binary. It's in the headers of the ELF executable, and we can actually see this either using the file command there or by using the readelf program, and we can see exactly the path to the interpreter. So the best way to check at least how the runtime linker loader is searching for libraries at runtime is, again, the documentation, the map pages. And here at the very bottom, and I'm using Ubuntu as reference, it's looking into lib and then user lib, which is where I actually installed the library. So now we know that exactly both at link time and at runtime, this is where those were retrieved. The executable itself, apart from the location of the interpreter, it also has encoded the dependencies that it needs at runtime. So in this case, I'm showing you two commands, either obj dump and or readelf as well, to see the needed. These are like, I think they're called dynamic tags of the ELF header. And each entry is a shared library that is needed by this executable. And what the runtime linker loader does is it tries to locate each library mentioned there, and then it's going to load those, and then it's going to see recursively what dependencies they do have, because there's multiple ones to actually launch this executable. A way of troubleshooting where at runtime libraries are being loaded is you can, or in the entire search procedure, right? You can do the ld_debug environment variable equals libs, and then you will see the dynamic linker loader will print exactly the paths that is searching for. An alternative as well, it's the LDD tool, which you may be familiar with if you work on Linux. And what this does is it invokes a dynamic linker loader. It runs the logic to load the libraries and actually stops, so it doesn't proceed with the execution. But word of caution here, because it's actually running the dynamic linker loader, it may actually initialize the code from those libraries. So I think the documentation does say to be careful when running this application, because you need to trust the binaries. So bear in mind that that's a concern. Another concern is this will show you all of the runtime libraries that are needed by the application, not necessarily the direct ones, but also by the program itself. So any indirect dependencies as well. So do keep that in mind. I remember, you may be familiar with what happened with XZ utils like several months ago. People were trying to determine, what was loading what. And I remember reading specifically, please don't use LLD for this. Please try to parse the headers instead. So summary so far is that we have two tools, the static linker, typically called LD, and we can cause it to be verbose to tell us exactly the search lines in the linker script. And the compiler may pass, and it actually does pass, additional locations for some internal libraries needed by GCC. And then we have the dynamic loader, which is ld_linux.so or ld.so. And we've also seen how to retrieve the default search path. It has some additional mechanisms that I'm not mentioning here, specifically the configure directory and the cache. So keep that in mind. And we have two ways of showing exactly how that search is happening. LDDebug is going to show us what is considered and why it is considered, all the paths. And LDD is just going to show us which libraries it found. So next thing, let's make our example a little more complicated. We have a library in a default location, right? So earlier I just showed you what happens when you have a library installed at the system level, but we may have libraries that are local to our project, so the linker is going to have additional information to be able to find it, both at runtime and at link time. We may be testing a different version of a library that's already installed in the system, or if using package managers that are not the system one, but also like Con, VC package, Conda, there may be other ones, Homebrew as well. You're going to need that. And other reasons as well, like having libraries where we cannot actually install them in the system. So let's try that. First, obviously, same example, but this time around, libfoo is installed in an arbitrary location that is not in the default path. So what's going to happen at compile time, or build time, sorry, is that the linker is going to tell us, hey, I cannot find that, right? And what we need to add to the GCC invocation in order to find it is -big L and the path. I think everybody's familiar with this, but the example is going to get more complicated, I promise. But then what happens when I try to run that executable? Well, I get the same error, but from the runtime linker loader for exactly the same reason, is two different programs, two different ways of telling them where to find them. So it's not gonna locate the library. So what can I do for this? Again, go to the documentation. We do have a few mechanisms specified by the loader to cause you to look into additional directories. One of them is the LD library path environment variable. I think this is very, you may be familiar with this. And I just initialize the variable, put the path to the library, and it's just going to work. And if I can confirm this by doing the debug environment variable as well. Another way of doing this, and bear in mind that because I mentioned that the executables are interpreted by LD.so, LD.so itself is an executable. This is what actually launches our application. So you can actually invoke it via LD.so with a flag to specify the path and not use any environment variables. Another one that's very commonly used, and this will be covered in more detail later as well, is the R path, called like runtime path, where you embed in the header of the ELF executable or library a path that the runtime linker is going to consider to find dependencies as well. So here you may see in yellow, we are forwarding big L to the static linker, and then we're telling the static linker as well, please embed this path into the binary. So it may look redundant, but it's actually like our path has a dual purpose in this instance. So what happens when I pass this flag is that the binary is going to have another ELF dynamic tag, in this case called run path, that is going to have the path to a library. So when we run the executable, there's no longer a need for a environment variable with the path. It will just work. But it will work on this system because we know that on this system, that library is installed in that location. So let's try to make it even a little more fun. I have two examples here where I have libfoo, and now I have a library that depends on symbols from libfoo. And I want to build both another shared library that depends on libbar and an executable, which is in green here, that also depends on libbar. And let's try. I'm creating the library. I'm telling GCC, please create a shared library with that file name, and I'm telling it where to find the include files. And this actually succeeds, right? And you may notice that I missed telling GCC, hey, please link libbar. Right. Well, what happened here is that it succeeded, it created the file, and it doesn't have a recorded dependency on libbar. If I were to link this against an executable, I would get missing symbols. And in that case, the linker would not know where to find them. Remember, this happens very, very frequently. So obviously, the solution is to tell, in this case, in the command invocation, please link libbar, and also tell the linker where to find it. Now, what happens if I try to do, and as you can see here, once I do that, the dependency will be recorded in the resulting library. So what happens when I try to do the same, but instead of producing a library, I'm trying to produce an executable? It's going to tell me that it cannot find libfoo. Bear in mind that we know my program only depends on libbar. So you could say that it's a private, that libfoo is a private dependency. So what's happening here is that at link time, the static linker is sort of trying to do the logic of the runtime linker and trying to load all the dependencies of everything that we have of all the dependencies of our dependencies, right? So it's telling us that there's an undefined reference to a symbol in libfoo. So the way to do this, and it's a bit strange, both libraries are in the same directory. So you would think, oh, I'm already passing minus big L opt foobar/lib. It should find it. If it's trying to locate libfoo, it should find it there. But it will not consider the directories here with minus big L for indirect dependencies. So what we need to do, and again, the RPath here has a dual purpose. RPath here is going to do two things. It's going to be used by the static linker to consider indirect dependencies of our direct dependencies. And it's also going to be stamped into the resulting executable for the runtime linker to consider. It's a bit complex, but both of the behaviors that I'm showing you are actually documented, and you can switch them on or off depending on what you want. The first one is that we saw GCC and linker will let us create a shared library even if there are undefined references to symbol, right? So that's why when I forgot to link the library, it still produced a library. And the other one is -L also specify that it only applies to direct dependencies, in this case, the ones that you explicitly link with minus little l. And for the other things, it's going to use rpath. So this is the resulting binary. Now that once everything succeeds, I have only a dependency on libbar. I have a library run path that points to the directory that contains both libraries. So what happens at runtime? Again, it cannot find libfoo. So it's exactly the same problem, but in a different place. And this is the documented behavior of the run path dynamic tag in ELF. So this is something that confuses and catches developers off guard. The run path dynamic tag, which is newer than an older tag, which is called rpath, not confusing at all, only applies to direct dependencies. So in this case, I'm only depending on libbar directly. The runtime linker is going to consider this directory for that dependency, but not for libfoo.so. We have a couple of solutions, which is either we use LD library path, so we will need to define an environment variable, or we tell the linker to please use the legacy rpath tag. The legacy rpath tag actually works as a stack, if I remember correctly. So if the executable contains the rpath tag, the legacy tag, then it's going to be considered even for indirect dependencies of other libraries. So rpath has been deprecated, I believe, maybe 2005 or 6, so that would be close to 20 years ago, because it had a higher priority than LD library path. So this was considered actually, to an extent, a security risk. And it wasn't until maybe around 2018 that some Linux distributions, in this case Ubuntu, decided to use the new dynamic tag by default. So when that happened, I remember you can expect lots of Stack Overflow tickets of like at runtime things not working properly. Now let's do another example where I'm still creating a program, but I change the implementation and I call functions that are in libfoo. But I forget to tell the linker when I try to link my program that I need symbols from libfoo. What's going to happen here is that I'm going to get an undefined reference symbol for the function that I'm calling from my program that is in the libfoo library. And interestingly, the linker is being actually super helpful. It's telling me, I know what those symbols are, right? But I'm not going to record a dependency on the library because you didn't tell me to. So that's why these two lines actually go together. The first line looks like an undefined symbol, but the second line is actually, well, I know where it is, so please add it. So that's what we need to do. And once we add the second library that we depend on, that's when we can successfully build this program. Now I'm going to be moving on to what happens for Apple platforms, which is actually very similar to Linux with some notable differences. The static linker is also called LD, although the implementation is completely different. And I think it was last year that they switched the implementation to something that I believe is a lot faster. The dynamic linker loader is called DLD now instead of LD.so. The file extensions are different. I'm going to be focusing mostly on dylib, which is the file extension for shell libraries, but SO is also used for loadable modules and frameworks and TBD files. Outside of the scope of this talk, because I didn't have enough time to cover this, but do please find me if you need more details about these things. For file inspection, we have two tools here, O tool and V tool. And if we need to change certain aspects of the headers of the binaries, then the install name tool can be used for that. So the linker search path, again, if we try to invoke, in this case, Clang on macOS, and we want to check where Clang is searching libraries to link, then this -v here is going to tell us. A difference with what happens on Linux is that this will only tell us the library search paths. It doesn't tell us where it's finding the libraries at link time. So that's something that I found interesting to say the least. Another thing is, like, instead of searching the system libraries in user/lib, it exclusively searches them inside the macOS SDK, which is provided by Xcode. It doesn't search the libraries that are in my file system, except for the user local lib folder, which, if I'm not mistaken, on a fresh macOS installation is completely empty. So it's up to the user to give contents to that folder. And once the program is linked, we can use otool minus big L to list the shared library dependencies. And here's a couple of things that are already different from Linux, is that instead of just seeing the leaf name of the shared library dependencies, some of them actually appear with a full path. In this case, the system library, libc++ and libsystem as well. So this is something that is specific to the Apple platforms, that each dynamic library has an install name. So rather than use the leaf name of the file to encode it as a dependency, we use a path, right? And this path can either be a full path, like I show you with the system libraries. It could be a leaf name as well, or it could be something relative to our path, which I'm gonna talk to about in a second in the next slide. So when I'm creating the library here, I could forward a flag to the linker to say, hey, please, the install name of this library is gonna be at rpath/libfoo.dilib, which is, this is very important for the runtime linker to determine where to find that library. And then another thing that I could do, instead of doing it at build time, I could modify or set it after it's been built. So the behavior of the runtime loader, it's going to depend, the search procedure is going to depend on what the install name of the dependency is. The ones in user lib, these are exclusive to Apple. So only Apple can place files inside this folder. RPath have a very similar behavior to the legacy RPath tag in ELF binaries, which is it's going to look in all RPath locations that you have across the chain that led to that dependency being loaded. And for historical and compatibility reasons, you can have an installment that is just libfoo.dilib, but this is no longer recommended as a thing on macOS or the other Apple platforms. So similar to what we had on Linux, where there's an environment variable to print the search procedure, we have this one on macOS, which is dild print searching. We can set it to a value that's non-zero, and it will just say, hey, this file needs this library, this is the install name, and this is the possible paths. And another thing that's interesting here is that the system libraries that are in user lib, it is telling us, that the files may exist there. These files are actually, if you have macOS, on recent versions of macOS, you will not find these files here. So what the linker does is it loads it from a cache. So it knows that those certain locations or certain libraries are exclusive to the operating system, and the files don't really need to exist. It just knows how to resolve them. And yeah, that's how the rpath libfoo.dilib is being resolved. Obviously, again, similar to what we have on Linux, we can set an RPath or multiple RPath entries when we generate the executable or the library, or we can do it after the fact with the install main tool. And if we run otool minus little l my program, we're going to see the different commands in the match o header here, and this would be a dependency on this library, and this would be an RPath entry, and it could be many dependencies and many entries. So let's go back to the example that we had earlier, where I tried to create a library that has a dependency, direct dependency on libbar, and an indirect dependency on libfoo, and I forget to tell the compiler, or in this case, or forward to the linker, that libbar needs to be linked. So on Linux, we know that this successfully produced a file that didn't encode the dependency. On macOS, is actually different. On macOS, what's going to happen is it's going to tell me right away, there's an undefined symbol, I couldn't find it, right? So obviously the solution would be to tell it to link library bar. Again, you can see in the manual pages for the static linker that this is documented. This is the minus undefined flag. The default is to error, but you can probably say either warner, suppress, or dynamic lookup. I think dynamic lookup would be the equivalent to what happens on Linux, right? So these are things that we actually see in Content Center, for instance. Some libraries may have issues that we try to build them for macOS, for Linux, for Windows. And sometimes we see things that work on Linux but don't work on Mac, or the other way around. And it's because of things like this, right? Because somebody somewhere forgot to express a dependency when creating a library. Another interesting thing about macOS, and this is perhaps another thing that I didn't mention, is that at link time, the linker doesn't need to find the indirect dependencies, right? And this is because of the two-level namespace that the Apple platforms use. On top of recording the symbols that are needed directly by our library, it also records which library is supposed to provide that symbol. So it's really not going to try to look for it at build time, and it will only happen at runtime. So next, we'll be moving on to Windows, which I would say is actually a little easier, but a little different as well. Instead of having a single file that is used both at link time and at runtime, we have two files. We have a .lib import library, which is not to be confused with a .lib static library, which is a very common problem, and also the DLL, which is exclusively used at runtime. And I think if you're familiar with Python and you use dependencies that load compile code, Python uses .pyd for loadable Python modules, but as far as I'm concerned, these are also DLLs with the same format, just specific conventions in which symbols or functions need to be defined. The tools here, we have CL for the compiler, link for the linker, at build time, and dump bin to actually introspect the contents of the file. I could not find a name for the loader, so I'm just going to be generically calling it the Windows loader. Difference between Windows and others is while the linker can be invoked by the compiler, what I've seen typically in build systems is that the linker is invoked directly. The inputs, there's also no flags for which libraries to link. They're just inputs as arguments to the linker. And you can specify the file name or the file paths. If you specify only the file name, the linker is going to search in two locations, either the contents of the lib environment variable, which I'm going to show you in the next slide, or you can actually pass flags with lib path for additional search locations that are prepended to the contents of the lib environment variable. Now, who sets the contents of this environment variable? If you're using the Visual Studio Tools command prompt, or the friendly name VC-vars, as some of us call it, this is set by that initialize script, and this will point to the library locations of the Windows SDK. So this is more similar to the macOS case, where the linker link time uses the locations inside the SDK, nothing in your system outside of that location. And you can pass to the linker this flag to cause it to print exactly how it's searching for, locating for these files. And if you're using Visual Studio, in the project, you can see the cplusplus directories, the library directories, and it will show you exactly the same thing. Now, what happens at runtime for the loader? There's a really good Microsoft documentation for this, and there's actually like 12 different cases of where to find DLLs. But in my experience, typically it's going to be one of three options. Either you have the DLL files, all of them needed right next to your executable file, or they're going to be installed in a system location, like typically like system32, or it's going to look in the entries in the path environment variable. So despite the fact, yes, we have documentation with all these cases, these are the ones that we typically see for C++ projects. Ways to list the dependencies of an already linked file. The dump bin /dependents, it's going to show us the library dependencies that are recorded for that binary, and this actually mentions all the DLLs. And in this test example here, I linked it against zlib, but also we're going to see some special libraries here, API-ms libraries.dll, and these libraries are not actually files in the file system. They're similar to what we had on recent versions of macOS, with the loader has some logic to actually derive where they exist in disk. And it may be a file that has a completely different file name, but it's some level of sort of indirection that's built into the loader as well. So what happens when we launch an executable and it's not found? Well, you're already familiar with the one on the top. So if I double click on an executable and the loader cannot find one of the DLLs, it's going to stop at the first one and it's going to tell me, hey, I can't find a DLL. But if you're operating from the command line and you launch the same executable, what's going to happen is nothing. You're going to get an empty line, and you're not going to know whether the program terminated successfully or not. So what you need to do is tell the terminal to print the last exit code of the previous command, and you're going to get this number here. And if you are like me and have bad memory, you're going to copy this, you're going to go to Google, and then one of the first three results is going to be the program could not locate a DLL, right? This is documented as a Windows error code. So I suppose, ends in 1515 if it's in decimal. I'll try to remember that. Hopefully you have better luck than me. If you want to troubleshoot exactly where DLLs would be loaded from when launching the application. There is a separate application that you have to download from the internet. It's kind of a bit outdated. It's called the dependency walker here. And you can see here that obviously it cannot find the zlib DLL. And additionally, it reports that all of those internal virtual DLLs that Windows uses also reports them as missing binaries. This doesn't necessarily fully surprise me. This tool is, as I mentioned, it's a little bit outdated as well, and it really doesn't have, it would need to be updated. It doesn't have the logic to know that, okay, these are actually not actual files in the disk. Alternatively, what you can do is use the Windows debugger. If you attach it to, I think the Visual Studio debugger and probably the separate Windows debugger as well, one of the things it's going to print is the images that were loaded, and those are the full paths of the DLLs and where it found them, if it did. And if it didn't find the DLLs, at least you know which one it couldn't find. Now, this covers the section of what happens on Linux, macOS, and Windows when it comes to finding libraries both at link time and at runtime. Hopefully that was useful. Now I'm going to be moving on to what happens a little earlier on that, which is what build systems do. So perhaps the first question that we can ask ourselves is, why should we bother having our build systems before build time trying to locate libraries? We already seen that if the linker doesn't find them, we will know, right? We could just, for instance, let's say I'm using OpenCV. I could just add that flag and let the linker fail during the build if the library cannot be found. However, you may see in your build scripts that you're actually looking for the OpenCV CMake package, or you have an AutoTools project that is using package config to check and find OpenCV ahead of doing the build. Now, why is this? Well, perhaps it's useful to error out early. It does save time. Imagine that instead of having a program of 2 lines and 1 function call as I had before, you are building Qt and you want to build a Chromium module, right? Would you rather know ahead of time that there are dependencies missing, or would you rather wait 1 hour and a half or however long in your system until the very end linking phase to know that a library was missing? So that's why it's, in a lot of times, most times, it's better to error out earlier. We may also want to perform additional checks on the libraries. Maybe there's ways of knowing what version we found and we're only compatible with a certain subset of versions. Is it the right architecture? This is actually a problem that I've seen in the past. Is it configured properly if, for example, you need a dependency build with specific capabilities or specific dependencies as well? It's also useful as well, like I mentioned here, you can do this on Linux, probably will work on Mac as well, linking against OpenCV core, but on Windows, the library names have the version number embedded in the file name. So you have to link against something different. And I don't know if anybody in the audience remembers the file names for the Boost libraries on Windows. So it's better to abstract that away in the build scripts to actually say, hey, I'm interested in Boost file system, instead of having to know exactly what the file name of Boost file system is in my platform or in my specific configuration. And one last reason where we may want the build system to locate shared libraries is to make sure that there is coherence between the flags that we pass to the compiler and the paths that we pass to the linker, specifically the paths themselves, not only other compiler flags like definition, so macros or something like that. Because it's very common if you're linking against different versions of libraries that are installed elsewhere in the system, especially in Linux, if there's a different version of the system, you may be doing the right include for your version of the library that you want to use at the compiler phase, and then the linker may be finding the completely wrong version, and anything can happen there. You may actually link but not run. It may link and run and not perform and crash, right? Or maybe link, run, not crash, and behave differently, right? So you really don't want to be in any of those scenarios. So what are the approaches that we see in build systems to locate shared libraries? So the first one that I can mention is, during the configuration phase, try and link a test executable that makes a call to a function in the library, tries to link it by knowing the name. You may see this specifically in AutoTools-based projects, right? It does require knowing the library names and knowing some functions as well. It will only work well, like I mentioned, because of the naming things, for libraries with well-known names. But also, it does bring the runtime loader into the build phase, which is problematic when you're cross-building. I actually seen libraries that cannot be cross-built because it will try to run executables like these probe executables, not only link them, but actually run them. And obviously, the binaries that I just cross-built, they're not gonna run on my machine. Another method is just try to find the library file ahead of time, and we do see this in the implementation of CMake find modules, right? Again, we do need knowing the library names ahead of time, and like I mentioned before, there's a lot of logic in the find boost module to actually derive what the file names are for your specific build. And another thing is like this will require us to an extent to replicate a linker search path. So I've seen actually, I think in CMake, if I'm not mistaken, there's a fallback search path that CMake detects which Linux distro you're doing, because different Linux distros have libraries in different locations as well. So it's actually interesting that this is happening, right? And the third method, which in my opinion is probably the more robust one, is find a package descriptor file that lives close to the libraries, and from those files can be used to derive the correct compiler and linker flags. In the most advanced cases, this provides a better abstraction because we only need to know a generic package name, and we may need to know, in the case of CMake, like target names as well. But it does require a convention to search for these files, like where do they live, and also a convention of how to call libraries. Like Google Test is called Google Test in some places and gtest in others. gRPC, I think I've seen all sorts of like lowercase, uppercase situations of those things actually happen here. And the three types of package descriptor files that I can think of are the package config .pc files, which are more flag-based. So this is actually the package config tool is going to give us flags, right? So it does have some downsides in the case that this is what prevents it from being more useful on Windows, for example, because you may have a library that you can link either using Clang or MSVC, but maybe they're using different flag formats, right? So that's a limitation. The CMake package, I suppose it's the wrong name there, the CMake configuration files for packages, right, that define imported targets. To me, this is really the most robust way we have at the moment, although the common package specification that was presented in CppCon last year by Brett Brown and Bill Huffman, and there was also a talk yesterday by Diego Rodriguez Lozada that works at Conan. This is probably going to be the future in the sense. I guess the only two downsides that I can think of for the CMake configuration files are two. One, that it's limited to CMake, which if you're not using CMake is going to be a problem. And two, that these files can actually contain arbitrary logic, including running programs and running code, right? So the idea of the common package specification is to address those two big concerns, is that it can be compatible across different tools in the ecosystem, but also be a descriptor rather than allow library and package maintainers to add arbitrary things. Now, where do we find the package descriptor files, the three that I mentioned? I could literally go on hours about this. If you use package config and you're cross-building and you're using a sysroot, right? Literally, that could take me a whole talk. So maybe for next year, I can do a talk about this. But what I want to talk about next is how CMake actually help us deal both with not only at the build time to actually get our binaries built, but at runtime, right? Especially when we want to run them locally or when we want to run ctests and run tests, right? So there are these two concepts that CMake uses specifically, and they're more helpful in platforms that support RPath, like macOS and Linux and any other ELF platform: the build tree and the install tree. The build tree is what your binaries look like on the machine that you just built them. Right? So CMake is going to pass wherever it can and wherever it knows by default, unless you change the default behavior, the RPath to the linker, so that the binaries that it creates are stamped with the full absolute paths of where the shared library dependencies are. Right? A prerequisite for this is that CMake knows about them. For some imported targets, it may not actually know if there's no equivalent imported target that has an indirect dependency recorded. So But for the most part, in my experience, actually works really well. So this is what allows developers to have libraries in any arbitrary location, build them locally on macOS and Linux, and actually be able to run the executables that they just built. Now, if you run the CMake install command, which is to produce to install the files in a final location or to produce something that you may give to other developers on different computers, is that CMake will patch the RPaths either by removing them completely and putting them in the final location, or replacing them with whatever the choice of the developer is. It could be a relative RPath, which would allow the package to be relocatable, or it could be a path to the full instant location where that package is expected to live. Now, in Windows, we're not that lucky, right? As I showed you before, when launching the executables, we're going to need DLLs, and either they are in the same folder as the executables or in the path environment variable. We don't have the facilities of ARPA to do this, right? So if we have shared libraries in non-default locations, then this is going to be a problem, and we will not be able to debug or run our tests. We're going to get those errors. The little window saying could not find a DLL, or worse, if you don't from the command line, then you're just gonna get like arbitrary error codes. So you can do additional things in your CMake lists. In this case, and this is an example from the professional CMake book by Craig Scott, I have defined a test, and I'm altering the environment modification property of the test such that when the test is invoked by ctest, it will actually have in the path environment variable the path that contains the DLL. However, you do need to know where the DLLs are, right? This may be relatively easy if you know where they are inside your project, but if you have them in arbitrary locations, then you are going to need some sort of CMake variable that contains this. An alternative to this, and this happens when you have either imported targets or other shared library targets inside your project, is, well, I can add the executable, I can do my targeting libraries, and I can have a custom command that runs as part of the build right after the executable, post build, right after the executable is built, to actually tell CMake, hey CMake, you know about targets, you know what the dependencies of those targets are. Please copy the DLLs for those targets right next to where the executable is being produced, right? And this is an example that is in the documentation for the generator expressions, but same as before, we had this limitation on macOS and Linux that CMake will only add the RPaths if it has enough information to do it. It's going to be the same here. And the reason I'm saying this is because for imported targets, it's not strictly necessary to have the property that knows where the DLL is, because the DLL is not really needed at build time. It's only needed at runtime. So you may encounter some imported targets that don't have this information. But what can we do on Windows to help with this DLL situation? Where if you're using package managers, C++ package manager, there are some integrations that help. So in Conan, we actually have a few options. We do have they're kind of like virtual environments. So if you load them, in this case, the Conan rat.bat, if you're operating on the terminal, this is going to set the environment variable, the path environment variable with the folders that contain DLLs coming from Conan packages that were built as shared libraries, right? Now, if you're using CMake 3.27 and a recent version of Conan 2, we also set this CMake variable here, which when CMake generates the Visual Studio project, it's going to initialize the path environment variable. I'm going to show you how that works in a second when you launch your executables through the Visual Studio debugger, right? And optionally, we also give you the option to copy the DLLs to the build folder during the generate method that gets called during Conan install. And we define in the Conan generated CMake toolchain, we do define a variable that contains all the directories that have DLLs coming from Conan as well, in case you need them for those other CMake snippets that I showed you. And if you're using VCPackage, if I'm not mistaken, the add executable built-in function is overridden with one that does something similar to this. So you're going to do add executable, and there's going to be a custom command that runs post build that will copy the DLLs at build time after it's built. So I'm going to show you how the Conan run sort of virtual environment works. I run command install to get my dependencies. I configure my build, I build it, and then what I can do is I can load this script into my terminal, and in the case of Windows, just running the script is going to modify your path environment variable, and then I can run my executable. And here we're lucky because instead of having a completely empty output, I do see the program is actually loading the zlib DLL correctly. If you're using Visual Studio and you're running it through Visual Studio, like I mentioned earlier, we do have the Visual Studio developer environment set up for you so that this can work. So hopefully these things help without the need to copy DLLs from across the content cache into your local folders, specifically for two reasons. And I have done this in the past. If you are not completely sort of trashing your build folder when the dependencies change, you may end up with copy DLLs from earlier runs that may be slightly inconsistent. And if you have a project that is large enough for you to decide that some executables live in different subfolders, then what's going to happen is you're going to have maybe to copy the same DLLs in different subfolders in your build, which is also not necessarily ideal, especially if you have a lot of dependencies or the DLLs are big enough. And the last thing that I want to talk about, just scratching the surface of this, is how to create relocatable bundles. So if from the build system point of view, we saw that in order to locate libraries, unless we use package descriptor files, we have to sort of replicate the logic of the static linker in order to create a bundle. On my bundle, I mean, I have my executable and I'm copying all the DLLs that my executable needs to, shared libraries my executable needs to run. Well, I need to sort of replicate the logic of the runtime loader. So the goal would be, I have my executable, it works on my machine. I need it to work on a different machine and maybe in a completely different path altogether. So, and the application, when it's run somewhere else, it needs to find its shared library dependencies when it's launched. So to me, there are two aspects to take into account when doing this, is to decide who is providing the shared library dependencies and where the application is going to live once it's installed on this other machine, right? And for the first aspect, we do have two approaches: either rely on a system package manager for systems that have one, or bundle the shared library dependencies with the application. And for the second aspect, which is where the application lives once it's installed, either it lives in a fixed location, so it's going to be the same path regardless of which computer it is installed on, or it's going to be on an arbitrary location that is decided by the person installing this at install time. So in blue, the system package manager giving you the shared library dependencies and the applications living in a fixed location. This is typical on Linux systems that have a package manager. And in green is typical in other systems like macOS and Windows, where you have your executable and you also give your users the shared library dependencies of your executable, and you also give them the ability to install your application in any location in their file system. So Linux System Package Manager, they are loved by Linux users. They do just work when it comes to installing things. And what happens is the external shared library dependencies are simply provided by other packages that as a packager, you don't have to worry about, except for you have to record which packages provide these dependencies, right? There are downsides, so they may be loved by users, but if you are providing your build binaries to other users, well, if you want this to work on different Linux machines, you may have to generate different packages, like Debian packages, RPM for other type of distros. You may have to generate Debian packages for multiple variants of Debian or different versions of the same distro, right? And what I've seen is like some vendors will set up a repository or an apt repository where you can configure it locally and pull a dependency as well. I think this is done, I don't know, Docker, Visual Studio Code. So this is actually done. What I've also seen is like sometimes those configurations don't really survive for too long. So those servers may cease existing or providing binaries in the long term. So for reproducibility purposes, it's not particularly great. And this is mostly Linux only, although you could argue that Homebrew or macOS does the same thing. Now, if you want to bundle the dependencies, your executable with your dependencies, you do need to find these dependencies first, right? You may also choose to give the runtime loader a helping hand. So on Elf platforms, you may choose to use RPAT, relative RPAT, to allow the user to sort of install the application anywhere they want. And on Windows, you really have no other choice but to place the DLL next to the executable. But first, we actually need to determine what to bundle, right? So our input is an executable, right? And we know it has dependencies, but we don't know what these dependencies are. But once we do know them, they're going to be one of these three categories. They're going to be system runtime libraries. They're going to be libraries that we built as part of our project, and they're going to be third-party shared libraries, right? It's the first category that you have to be careful. We typically don't bundle these because they're already part of a target system. And in a lot of cases, we cannot bundle them because it would be a security issue, or they would just not work because the OS would not let us override a particular library with a name. As for what format to use when we generate these relocatable bundles, it could be an arbitrary folder where I decide, okay, this is my executable, these are the libraries, and just use relative RPAT. Or some platforms do have specific formats. On macOS, we have the .app app bundles as well, which is a folder with a specific pre-specified structure. We have app image on Linux, which, if I'm not mistaken, is not that common, but it's used. On Android as well, we do have the APKs, and if you do have native libraries, there's a specific subfolder where you can install them. As for tooling to generate these things, well, I mean, if you're on macOS, you can use Xcode as well. It would do it for you. But from a more generic perspective, I found sort of two approaches. On Linux, we can rely on the runtime linker to get that list. I showed you earlier, you can use the LDD tool to get a list of all the libraries, and then you have to apply some logic of, which one is a system library that I should never bundle, and which libraries do I copy, right? So based on the output, either the library name or the location, you're going to determine that. And I've seen this implementation used in a tool called Linux Deploy Qt that, despite its name, it actually lets you bundle not only Qt, but all the other dependencies. And I did see logic to find the sort of invoke LDD, determine which are system libraries, and then copy everything else, right? The downside is that this will only work on Linux platforms that have Linux or other platforms that have LDD. And it uses the actual loader, so it may not be helpful when you're working with cross-build binaries because you're not going to be able to run LDD on those. The second approach that I've seen, and I'm almost finished, is sort of replicating the logic of the runtime loader. That is, you're going to start from your file. You're going to use those tools that I just showed you to inspect the header of those files and get what the encoded dependencies are. You're going to try to find those dependencies, find their dependencies, and once you have the list, then you're going to go through the same process of discarding some of these and not bundling them at all, right? So this is an example of Go app image. The tool here, what I saw is like, oh, yeah, they do have those paths that are typical in Linux hard-coded in there. And they also had a list of file names of things that should never be bundled for system libraries. You can more or less do the same with CMake. In recent versions as well, you can use the install runtime dependency set. So given an executable, at install time, when you invoke CMake ---- install, well, you can try to replicate that logic. I found some rough edges there, so believe me, it's really difficult to replicate the logic of the runtime loader. And these are some of the patterns that you can use to discard the things that should not be either bundled or looked any further, right? So it's not that easy. It works, but your mileage may vary, as people say. And if none of this works, then lying to the process is an alternative if you're on Linux, right? What this is like, containers are processes. We're launching a process, and when that process requires files from the file system, the kernel, instead of locating files in your host machine, is going to be providing them from inside a container. So this actually simplifies things a lot by the kernel creating this illusion around the process. And if everything else fails, just link everything statically and ignore everything I just told you. Any questions? Yeah, if you could go to the mic, please.
Hello. So recently I was trying to distribute a Mac app written in C++ without using Xcode, because why would I? Using CMake, and I think CMake can produce that directory structure.
Yeah.
And but I couldn't get the executables to find the libraries next to the executable, because it was either an absolute path or R path, which I think depends on an environment variable,
Yeah.
or relative, but relative to the
Yeah.
working directory, not relative to the executable itself.
Yeah.
I couldn't get it to use at executable path.
Yeah.
And is that because you think because CMake, as you said, replaces the RPath with developer choice when you do -- install?
Well, so the app bundles of macOS are special in the sense that I think the loader for those, it's only going to let you load them from the frameworks folder. So your executables, I think they go in content/macOS.
Yeah.
They need to have an RPath that points to the add executable path /./frameworks, right? That's the RPath of the executable. And then all of your shell library dependencies, they need to be in the frameworks folder. And that should do it. Sometimes the reason it wouldn't work is because the gatekeeper will prevent you from loading libraries that are not contained on the app and not a system library. So that's probably why. It is undocumented as far as I've seen, but I've seen it happen, loading libraries on macOS from the current working directory. So this is not how you would do it. You have to put them in the frameworks folder and then tell the executable to look there in relative path.
Okay, thank you.
But if you have any help, I'm happy to help you after this as well.
In the end, I linked everything statically.
Oh, perfect.
Hi, thank you for the talk. Really nice. You mentioned trying to shift a lot of this runtime linking logic or trying to emulate it in some way in the CMake configuration step.
Yeah.
Can you kind of talk about how does CMake target aliases fit into that equation?
The CMake target aliases is just like different names in which you can refer to a target that has a different name elsewhere, right? When it comes to imported targets, that's when CMake can help, because if CMake has enough information to know that an imported target has an indirect dependency that for whatever reason is in a different folder, then CMake can actually add it to the RPath or RPath link. I didn't mention RPath link, but it's used only at link time. And that will help you actually run the binaries. But I don't think it's related to the target aliases.
Okay, got it. Thank you.
No worries. Perfect. If you have any more questions, feel free to find me and I'll be at the Conan booth today. Thank you so much for coming.